week 9 problem solving session of differential equation for engineers. Myself Guru Bachar from Department of Mathematics, IIT Jodhpur. I am working in the broad area of fractal geometry and dynamical systems. In today's problem solving session, we mainly focus on the solution of the wave equation. It might be the infinite, you can say infinite length string, or you can say it might be a semi-infinite. So we deal with all these kinds of cases. So let me introduce the question number 1. So in first question, we deal with the infinite case. So there might be two cases, infinite or semi-infinite. So first one is infinite. Question number 1, find the solution of the initial value problem. And what is the initial value problem? We have given the wave equation utt minus 3 times of uxx is equal to 0. Since I was saying infinite case, so that means x must belongs to r and t must be greater than 0. Since it's a time, so time is always greater than 0. And our initial condition is given as ux0 is equal to some x sin x, where x is any real number, and ut x comma 0 is given as cos 2x. Again, x is any real number. So we have to solve this initial value problem. Why we are saying it's an initial value problem? Because you have taken t equal to 0. So these are the initial conditions you have given. And when we dealing a semi-infinite case, then we'll get to know why we'll say there that the given problem is a infinite initial boundary value problem. So we have to deal here with this infinite case. So if you will observe from the original equation, in the original equation we have given that 2tt minus c square uxx is equal to 0. I am writing the general infinite case for this wave equation, and t is greater than 0. So in this scenario, and suppose this is given as fx, where x is any real number, and ut x0 is equal to some gx, where, so in this case our solution is determined by D'Alembert's formula, or you can say D'Alembert's solution is given as, so D'Alembert's solution is given as u x t is equal to half f of x plus c t plus f x minus c t plus, there is one more factor, so that we write in the following manner. Other factor is 1 by 2c x minus ct2 x plus ct gs ds. So this is our general solution that we know of our general general infinite case. So here you can observe that what is the value of c? The value of c is under root 3. Since c square is 3, so c will be under root 3. And value of fx will be x sin x. And while the value of gx is cos 2x. So what you have to do? You have to substitute all the values and calculate this uxt. So try yourself first. So let us proceed this one with this general D'Alembert solution. So we have to calculate these two values. So what we do for the sake of ease of calculation, we will explicitly calculate both of them value. So f of x plus ct plus x minus ct. This will be x plus under root 3t, since our fx is x sin x. So sin x plus under root 3t with addition of this x minus under root 3t sine with this angle. So this will be x minus under root 3t. Okay, so here what we can do, we can expand this sin x plus under root 3t and sin x minus under root 3t in the manner. So x plus under root 3t, this will be sin x cos under root 3t plus cos x sin under root 3t. Okay, one factor is this, and another factor will be sin x cos under root 3t minus cos x sin under root 3t. So we got these two factors. If you will observe smartly, when you multiply x with both the factors, this this term is a positive sign and this term is with negative sign. So if you will take x common and you will add them, then this will be 2 times of sin x cos under root 3t. While if we talk about this factor under root 3t, so in case of under root 3t, this is a positive sign and here is also positive sign, so we don't need to worry about this. What about this one? This is with negative sign, this is with positive sign, and negative negative will become positive. That means the first term is going to be cancel out and second term will has to be the double. So that means 2 times of under root 3t cos x sin under root 3t. So if you will, from here you will see half of f of x plus ct plus x minus ct. This will come out to be x sin x cos of under root 3t plus under root 3t cos of x sine of under root 3t. So one factor we have solved. Now we have to solve the another factor, that is x minus under root 3t to x plus, in fact here we should write c in place of under root 3, g s ds. This will come out to be x minus under root 3t to x plus under root 3t, and our gx was cos 2x, so here it will be cos 2s ds. So this will come out to be x minus under root 3t to x plus under root 3t. So we should integrate here in this step only. So this will be 1 by 2 sine 2s. So this will be x minus under root 3t to x plus under root 3t. So if you will solve this, half sine 2x plus 2 under root 3t minus sine 2x minus 2 under root 3t. So this is our expression, and if we try to solve it, so what we will get, this is sine a plus sine b minus sine a minus sine b. So sine a plus b you can say. So here it would be half of sine 2x cos 2 under root 3t plus cos 2x sine 2 under root 3t. Okay, now with negative sign, minus sine 2x cos 2 under root 3t, and here we lose negative sign, but outside is also there is negative sign. This will be plus cos 2x sine 2 under root 3t. So this is our whole expression. So from here two terms will cancel out, so you will get cos 2x sine 2 under root 3t. Okay, now we can substitute these values in the given solution. So uxt will be, from the first factor we know that this is x sin x cos under root 3t, so I am writing from here. So x sin x cos under root 3t plus under root 3t cos x sin under root 3t. So one factor is contributed by the first term, and the other one factor is contributed by this integral form, which is cos 2x sine 2 under root 3t divided by, since it was division, it should be divided by 2c, and the value of c is under root 3, so this will be our general solution, or you can say the solution of the given IVP. So this is the solution of the given IVP. Okay, so here we have discussed this infinite case. Now let us move to semi-infinite case. First one is find the solution of the IVP, or in fact, since we are dealing with semi-infinite case, so here it should be initial boundary value problem. I will let you know why we are saying we are taking this condition boundary value problem. So equation is wave equation is given as 4 times of uxx equal to 0, where x is positive and t is also positive, while ux0 is sine square x, where x is positive, ut x0 is 0 for x is positive, while u0t is given as 0 when t is positive. So if you will observe smartly here, this is the given initial condition and this is your boundary condition. How? So it is like this. So you are taking x to be only positive. So you know for this kind of condition, but since we want our solution to be valid on whole R, so what we'll do, we use this condition that is at u0t, that is when this x is 0, what is the value of this boundary at this boundary. So we have taken this boundary condition, that is why we are calling these kinds of system as initial boundary value problem system. So let me first recall what is the solution of this kind of system by D'Alembert's method. Okay, so here we have taken extra boundary condition, so it has a special name, or you can say, so it can be also obtained from this D'Alembert solution. How? So in general, utt minus c square uxx is equal to 0. So ux0 is some fx, utx0 is some gx, and u0t is 0. Here x is from R, t is greater than 0. Sorry, since we are dealing with semi-infinite, so x must be greater than 0, x is greater than 0, x is greater than 0, and t is greater than 0. So this is your semi-infinite general case. So in this scenario, we will get the D'Alembert solution in this form, or you can say D'Alembert solution can be modified in the following way. So there will be two cases, uxt. So how these two cases are divided, let us see here. First one is half f of x plus ct minus f of ct minus x. This is your first part, plus 1 by 2c of ct minus x2 ct plus x gs ds. This solution is valid for the case when x lies between 0 to ct, while f of x plus ct plus x minus ct, since the other case will be x greater than equal to ct, that is this is going to be positive, so we have to deal with this earlier D'Alembert solution. So 2c x minus ct to x plus ct gs ds. So this is our modified D'Alembert solution. Here, if you will observe, we will deal this f and g by doing its odd extension, or you can say we are extending our solution in a odd function manner. So in this case, the value of c is 2, the value of fx is sine square x, and the value of gx is 0. Okay, so we have to substitute these values and calculate the terms. So for each case, so I am solving first of all explicitly. Suppose I am solving this case 0 to x less than ct. Here the value of c is 2. So this will be u x comma t is equal to half of sine square x plus 2t. minus sine square. Here you will get 2t minus x plus 1 by 4 of x 2t minus x2 x plus 2t 0 times ds. Since gx is 0, so from here we have to solve these two values. So this is given as half. So if you will observe from here, you will take minus sign common. This is again going has to be sine square 2t minus x itself. So if I will open up this one, this is sine x cos 2t plus cos x sine 2t. This quantity square, okay, with the negative sign of, and other square will be sine 2t cos x with negative sign sine x cos 2t its whole square. So this is our rest of the quantity. So if you will observe that whenever you will deal with a plus b whole square minus a minus b whole square, you will left with only 4 times of ab. This is the case here also. So half 4 times of sine x cos 2t cos x sine 2t. And if you will arrange them in a good manner, so 2 sine a cos a is sine 2a, so this will be sine 2x, and another expression will be cos, or in fact sine 4t divided by 2. So this is the case when our this x lies between 0 to ct, or you can say here 0 to 2t. So what if the other, we will talk about the other case, that is when x is greater than ct. We can say equal because we will maintain the, while finding the solution in the class, we maintain the continuity of the function or our solution. So here uxt will be half sine square x plus 2t plus sine square x minus. So here we don't need to take 2t minus x because we are working x greater than equal to ct, then that is x minus ct is never it is a positive side of the function. So from here 1 by 4 x minus 2t to x plus 2t 0 ds. So half. So from here what you can do, you can use cos half angle formula. So this will be 2x plus 4t divided by 2, and from here 1 minus cos 2x minus 4t divided by 2. So from here you will get half, and this half of becomes 1 minus cos 2x plus 4t with negative sign, or you can say this will become positive 2x minus 4t divided by 2. So if you will apply here cos a plus cos b plus cos a minus cos b, so the second terms will cancel out. You will left with only the first term, that is 2 times of something. So this will be cos 2x cos 4t. Okay, so ultimately then your solution will be uxt will be, that will be divided into two cases. From the first case we are getting half of sine 2x and sine 4t. This is the case when this x lies between 2t, and the other case is half minus cos 2x cos of 4t divided by 2, and this will be the case when x is greater than equal to 2t. So this is the is the solution of the given initial boundary value problem. So in this case, we got somewhat easy calculation because our gx was 0. What if our gx is non-zero? So that is considered in this third problem. In the third problem, find the solution of initial boundary value problem, and initial boundary value problem is given as u dt minus 4 times of ux6 is equal to 0, where x is positive, t is positive, and ux0 is given as sin x with x is positive, utx0 is given as x square where x is positive, u0t is 0 where t is positive. So we have given this similar kind of the above equation. Here our c value of c is 2, fx is sin x, and gx is x square. So we need to deal with two different cases: x is greater than ct or x is less than 2t. Here c is 2, so try at your own, then we will discuss. So let us continue here with the two explicit cases. The first one is when our x lies between 0 to 2t. Okay, so let me recall. When x lies between 0 to 2t, what is our solution? So our uxt is, in this scenario, half of f x plus ct, that is 2t, minus f of 2t minus x plus 1 by 2 c, that is 1 by 4 2t minus x to x plus 2t gs ds. So if you will substitute the value of this fx, this is sine x plus 2t minus sine 2t minus x. So this will be 1 by 4 2t minus x to x plus 2t. Here gs is s square ds. So if you will observe, sine is an odd function, so this will be nothing but plus sign of sine 2t minus x. Either you can do in this manner, or you can directly open up this sine a plus sine b, or sine a minus sine b. So this will be half sine x cos 2t plus cos x sine 2t. One quantity is this, then sine 2t cos x, and minus minus will get plus, so this will be cos 2t sine x. So this is your first part, and the second part will be s cube divided by 3, and 1 by 4 is outside, so this will be 2t minus x, x plus 2t. So from first factor, the two term will cancel out. Which two term? So this is a negative sign, so sine 2t cos x, these two will cancel out, and you will left with the 2 times of the other two quantity, and 2 is the denominator in the outside, so you will left with sin x cos 2t. Okay, so next one is 1 by 12. So if you will observe in the smart manner, that a plus b cube minus b minus a cube, what is the value of this quantity? So this will be a cube plus b cube plus 3a square b plus 3ab square, with negative sign, a cube b cube. So this will be minus 3b square a. So since there is minus sign outside, so this will be negative 3ab square. So from here, this a cube will cancel out, b cube will cancel out, and 3a square b. So here I think I wrote 3a square b, so this will cancel out. So you will left with only So from here you will left only with the part, so a cube minus b cube, so this should be plus b cube. So these two terms will not cancel out, so this will be b cube or this will be plus b cube. So we left with 2 times of b cube plus 6 times of ab square. So from here you can get the value of this. Here the value of a is x and b is 2t. So b is 2t, so this, therefore this will be 2 times of 2t whole cube plus 6 times of a, that is x, and 2t square. So if you will solve it, sin x cos 2t plus, so from here 2 to the 4 to the 8, 16, and 16 divided by 12, so it will contribute 4 by 3 t cube, and the next factor is 2 to the 4, 4 6 is the 24, that is 2 times of x t square. So just let me verify this one. So this is the case from x 0 to t. This was question number 3. So just a second. X cube by 6, yes, correct. And another cases. So here this was the case a plus b whole cube and b minus a whole cube. So we did some little missed one step here. So this was b minus a cube. So b minus a cube means this will be minus b cube, this will be plus a cube. Okay, and this will be with negative sign, so outside will make it positive. So 3b square a, and another one factor will be positive, then this will make negative 3ba square. So let us judge again which quantity will cancel out, and this will help us in the second part also. So from here if you will observe that b cube will cancel out and 3a square b will cancel out, this will cancel out, then you will left with only 2 times of a cube plus 6 times of a b square. So here you will be 2 times of a cube means 2 times of x cube, so this will be 2 times of x cube, and from here you will get 6 times of ab square, that means 6 times of x, and b is 2t square. So this will give us x cube divided by 6, and rest will be 2x t square. So this is your solution for the first case. Now what will be the second case? So when, since we are maintaining continuity at 2t, so we may consider here x equal to 2t also. So from here your solution was uxt is equal to half f of x plus 2t. Since x minus 2t is positive, so here we don't need to we can take the infinite string solution, or so you can say infinite solution, infinite case solution. So 1 by 2c x minus ct to x plus ct and gs ds. So from here you will get half sine x plus 2t. Since here we are dealing with, we are putting already the value of c, here we should put the value of c, sine x minus 2t plus 1 by 4 x minus 2t2 x plus 2t s square ds. So from here you will get here sin a minus sin b plus sorry, sin A plus sin B plus sin A minus sin B. So obviously the first term will remain and the second term will cancel out, since both are doing we are doing addition of both. So you will get sin x cos 2t, and outside there is a 2, so 2 and 2 will cancel out. For the other side factor, 1 by 4 x cube divided by 3, so x minus 2t, x plus 2t. Now, since in the above expression we judge how a plus b cube and b minus a cube will behave, so in the same scenario, the left two terms will be our answer for the following equation. So what will be that? So a cube will cancel out, you will left with the 2 times of b cube. The other quantity will be 3a square b. From here 3a square b, uh, that will be with negative sign, and outside is there also negative sign, plus 6a square b. So I think this will be the case. Okay, so from here then you will get sin x cos 2t. Outside there is 1 by 12 and the value of b is 2t, that is 16 by 12, that is 4 by 3t cube. The other quantity is 6 times of a square, that is x square, into 2t, that is 12x square t, divide by 12. So you will left x square t only. So these are the two cases of solution. So first one is sin x cos 2t plus x cube divided by 6 plus 2x t square. This is the case when 0 x lies between 2t, and the other case is sin x cos 2t plus 4 t cube divided by 3 x square t, x greater than equal to 2t. So this is your solution, is the solution of the given initial boundary value problem. So this is the case when we have done the odd extension of this fx or gx, or you can say odd extension of your solution. What if when you do even extension, or you want to do even extension of the solution, so you need some different boundary condition, and which can be covered in the next question, that is question number 4. Find the solution of the initial boundary value problem, and the problem is given as utt minus uxx equal to 0, where x is greater than 0, t is greater than 0, while your ux0 is given as cos of pi x by 2, where x is positive, and utx0 is given as 0, where x is positive, and u0t is given as 0. And here, since we want our even extension of solution, we will take ux at 0t rather than taking the earlier case u0t equal to 0. So this is your given wave equation, and these are your initial condition, and this is your boundary condition. So in this case of in this scenario, what we have to do, again we have to divide two cases, when x is greater than 2t or when x is less than 2t. So let me recall the solution in this kind of scenario. So the general equation, wave equation, is like this, where your x is positive and t is greater than 0, while ux0 is some fx, where x is greater than 0, utx0 is some gx, where again x is greater than 0, and 0t is 0, where t is greater than 0. So this is our, you can say, general wave equation for semi-infinite case, where we want to extend our solution to be in even function category. So the D'Alembert, or you can say modified D'Alembert, which comes from the infinite case solution. D'Alembert's solution is, so it is defined as uxt, which will be equal to half of x plus ct minus x. You may observe that here there is only positive signs. The reason is we are extending in even function. If it was odd function, so here it would be negative sign. So plus, so this expression is a little bigger manner, so let me rearrange it. So the integral will be divided into two cases, 1 by 2c, 0 to x plus ct gs ds, with negative sign, 0 to ct minus x gs ds, and this is the case when x lies between 0 to ct, while when you deal with x greater than ct, that is x minus ct is positive, so that case will be dealt in the same way of the infinite case. So it is like this, 1 by 2c, the integration x minus ct to x plus ct gs ds, where x is greater than equal to ct. So we need to deal with these two cases in this following problem. So first case is when our x lies between, so here the value of, you will observe the value of c is 1. So first of all let me mention what is the value of c. So the value of c is 1. The value of fx is cos pi x by 2, and the value of gx is 0. So in this scenario we know all these three values, and we have to substitute these three values and calculate what is our solution in all the two cases. So first case is when x lies between 0 to t. So in this scenario our first factor will of the solution is half of x plus ct and f of ct minus x. So uxt is half of x plus ct, that means cos of pi by 2 x plus t. The value of c is 1, plus cos of pi by 2 x minus t. So here ct minus x, that means here should be t minus x. Next factor will be 1 by 2c, that is 1 by 2, 0 to x plus t, since the function g is 0, 0 ds, plus t minus 0 to t minus x, the function is 0, so it will be like this. Okay, I have just substitute the value of g, c and f. So the second term will be ultimately going to be 0, so this will not contribute in our solution. So we left with the first term. So if you will observe here, so this is nothing but cos pi x by 2 pi t by 2 plus cos pi t by 2 minus pi x by 2, these two values. So this is cos a plus b plus cos a minus b. So if you'll expand this formula, the only first term will contribute in the solution, that is 2 times of cos pi x by 2 cos pi t by 2. So I am writing it directly, you may solve at your own. 2 times of cos pi x by 2 pi t by 2. So these two 2 and 2 will cancel out. You will left with cos pi x by 2 cos pi t by 2. So this is the solution for your first case when x lies between 0 to t. What if when x is greater than equal to t. In this scenario, your uxt will be 1 by 2 f of x plus ct, that is cos pi by 2 x plus t plus cos pi by 2 x minus t plus 1 by 2c of x minus t to x plus t 0 ds. So from here you can directly say this term will be equal to 0, and from these two terms again you are going to get the same value, that is cos pi x by 2 cos pi t by 2. So from both the two cases we are getting the same value of the solution. So ultimately what I can say uxt is equal to cos pi x by 2 cos pi t by 2 when x is greater than 0, t is greater than 0. This is our general solution, or you can say this is our solution of the given, is the solution of the given initial boundary value problem. There is one more observation that you can see from the solution. So in the first question you get the solution uxts in this form. So in these values you can substitute the initial conditions and you can verify that your solution satisfy the initial conditions or not. Or definitely, since we are finding this from the D'Alembert solution, this must satisfy the initial condition, or you can say boundary condition also in the further questions. So this will definitely satisfy our D'Alembert solution or initial condition and boundary condition. So these all are the cases of infinite case, semi-infinite case with even extension or odd extension. Now the next question we deal with transformation of canonical form, so that we can convert in the wave equation into some canonical transformation, and then we can find out the solution or not. So let me write question related to it. Question number 5 is, consider the PD. We have given this PD utt minus alpha times of utx plus beta times of uxx equal to 0, where x can be any real number and t must be positive. And here alpha and beta are such that they satisfy the following equation: lambda plus beta equal to 0. And this equation has two distinct roots, c1 and c2, from real number. So we have given a PD and we have given what is this alpha and beta satisfying this equation, which has two distinct real roots. So what we have to do then, use the transformation variables, and transformation variables are defined as xi is equal to x plus c1t and eta is equal to x plus c2t, to reduce the above PDE to u xi eta equal to 0. So we have given the PD in the form of this x and t. Now what we are asking for, we are asking to reduce this PD into the canonical form, where the canonical transformation are as x xi equal to x plus c1t and eta equal to x plus c2t, and we have told that this c1 c2 are nothing but the solution of this quadratic equation. Now this is the this is not the new question for us, it has been done in the last class, so we have to just recall that approach. So if you will remember from the last class, if we have given suppose x plus c1t, eta is equal to some transformation x plus c2t. Our system is in the form of derivative with respect to x and t. Now we have to convert the system into the derivative, partial derivative with respect to xi and eta. So what you will do, you will differentiate. First of all, calculate this xi x. What is the value of xi x? This will be 1. And the value of xi t will be c1. Similarly, the value of eta x will be 1 and the value of eta t will be c2. Okay, so you got these values. Now what we will do, you will substitute ux in terms of u xi and u eta. So from the chain rule, you know that u xi x plus u eta x. So from here you will get the value of xi x is 1, so this will be u xi, and the value of eta x will be 1, so u eta. So you got the value of ux in terms of u xi u eta, but observe we need uxx and uxt. So then we have to differentiate it again. So first of all, you differentiate the whole quantity with respect to xi. So this will be u xi u eta xi into xi x plus, then you have to differentiate with respect to eta, u xi eta, u eta eta, eta x. So xi x and eta x has value 1, and since we are working with the continuous partial order derivative, then u xi eta and u eta xi will be same. So this will be 2 times of u xi eta plus u eta eta. Okay, you know one value of uxx from here. Next is what you can do, you can calculate uxt, and uxt is nothing but utx. As I told you, we are working with the continuous partial or second order partial order derivative. So from here, when you will differentiate with respect to t, so first u xi plus u eta xi into xi of t plus, next quantity will be u xi eta u eta eta into eta of t. So the value of eta of xi of t, if you will observe, it is c1 and eta of t is c2. So from here you will get c1 u xi plus c1 plus c2 u xi eta plus c2 of u eta eta. You got the second term. What you have to calculate now? utt. So to calculate utt, you have to first calculate ut, that is u xi t plus u eta eta t. So from here you will get c1 u xi plus c2 u eta. In the same way, when you differentiate it again, you will get c1 square u xi plus 2 times of c1 c2 u xi eta plus c2 square u eta eta, equation number third. Now you know the value of uxx, uxt and utt in terms of xi and eta. What you have to do, you have to substitute all these values in this given equation. So let us do that. So our given equation is utt minus alpha times u. So let me just first verify this equation. So as I was thinking, there is a little ambiguity on typo, you can say. So this will be plus sign. So here this is a plus sign. So plus utx plus beta times of uxx equal to 0. Now from 1 and 2 and 3 we have to substitute all these values. So from 1 you know that this value is c1 square u xi xi plus 2 c1 c2 u xi eta. As we have done in the earlier classes, what we do, we write the terms in a column wise manner so that we can calculate their value. Or you may do like this, row wise. You can write in the row wise form. So it will be 2 c1 c2 u xi eta and c2 square u eta eta. So this is your first term from utt. Now from utx you have to multiply this with alpha. So this will be alpha times c1 u xi xi plus alpha times c1 plus c2 u xi eta plus alpha times c2 u eta eta. Okay. Now the third term will be multiplied by beta, that is beta times u xi xi. So here it is xi xi plus 2 times of beta u xi eta plus the third term will be beta times of u eta eta, this whole equal to 0. So if you will observe that, and or you can say you will take the terms common, so this will be alpha c1 square alpha times of c1 u xi xi. This is your first term. The second term is alpha c1 plus alpha c1 so here it is 2 c1 c2 plus alpha times of c1 plus c2 plus 2 times of beta u xi eta plus the last term will be c2 square plus alpha times of c2 plus beta times of u eta eta equal to 0. Now what you have to do, you have to think what is c1 and c2. You know that from the question, c1 and c2 are the two distinct roots of this equation. So if c1 and c2 are distinct roots of this equation, so because c1 and c2 are, let me just, so now maybe this file will work properly. So c1 and c2 are two distinct roots of lambda square plus alpha lambda plus beta equal to 0. So that means for the value of lambda equal to c1 and lambda equal to c2, this must satisfy the equation, that is c1 square plus lambda times of c1 plus beta, this must be 0, and c2 square plus lambda times of c2 plus this beta, this also has to be 0. So this is your equation number 4 or equation number 5. From both this you can say your star equation will transform to, so by equation number 4, by equation number 4, 5 and this equation number star, but you will get, you will get 2 c1 c2 plus alpha times of c1 plus c2 plus 2 times of beta, this whole quantity into u xi eta equal to 0. Now you know this value, so you just need to say that this is a non-zero quantity, so that the left quantity will be 0, because product of two numbers is 0 if and only if one number you can say it is non-zero, then another number has to be 0. So what you will do, you will just do a little manipulation in the form C1 plus C2 plus 2 beta equal to. So you know that this C1 C2 satisfy this given equation. So this minus alpha will be the sum of roots and this beta will be product of roots. So we need to just use that C1 plus C2 is nothing but minus alpha and C1 into C2 is beta. So we just substitute these values to get some relation between C1 and C2 and to justify this quantity is a non-zero quantity. So from here you will get C1 C2 with negative sign C1 plus C2 whole square plus 2 times of C1 C2. So from here this will be 4 times of C1 C2 minus C1 plus C2 whole square. So from here if you will observe that this is nothing but C1 minus C2 whole square. So can we say from here this is a non-zero quantity? Yes, we can say. Why? We have given that these are the distinct roots. That means C1 cannot be equal to C2. So suppose if C1 equal to C2, what will happen? If C1 equal to C2, then in that scenario, xi will be nothing but directly eta. But we cannot transform in this following manner because there will be no linearly independent transformation. So therefore we have to consider the case C1 not equal to C2. Since C1 not equal to C2, that means this quantity is a non-zero. Hence what we can say that u xi eta must be equal to 0. Thus we want to prove in this particular question. So till now we have proven that how this canonical form transformed for this wave equation. Now the natural question arises, what can be the solution output from this equation? So that will be covered up in the next question, that is question number 6. So in question number 6, find the solution of the PD. We will deal with the same PD that we have taken in the question number 5, that is UTT plus alpha times UTX plus beta times UXX equal to 0, where X is any real number, T is any positive quantity, and where alpha and beta are such that lambda square plus alpha lambda plus beta, this is equal to 0, has two distinct roots C1 C2 from real number with, here we have given some initial conditions, with initial conditions, and initial conditions are as follows: ux0 is equal to fx, and the another initial condition is utx0 is equal to some gx, and here x is any real number. So from the earlier case you know that your transformation is valid and your transformation is giving you u xi eta equal to 0 0. Now what we have done, we have a step ahead, we have given the initial condition. Now we, with the respect to this initial condition, we have to find out the solution in this form of fx and gx. So try this one, then we will discuss it. So let us start discussing this solution of this given PD. So we know that from excuse me from question number 5, or you can say from the solution from problem number 5. Problem number 5, we know that the canonical transformation of this equation is nothing but u xi eta equal to 0. Now if you try to find out the solution, so first of all here the highest derivative we are with respect to we are doing with eta, u eta equal to 0. That means that is u xi must be some function of, you can say directly, xi. Okay, now what you have to do, you have to find out the value of u xi eta. For this, what you will do, you will integrate this phi xi with respect to this xi plus some function of eta. Okay, so this is again a function of xi. So what I can say, u xi eta is nothing but some function of xi plus some function of eta. Okay, and what was the value of xi? Value of xi was x plus c1t, and value of eta was x plus c2t, because we know this. So our solution uxt must have the form x plus c1t and g will be x plus c2t. So this is your uxt. Now you have to set you try to satisfy this initial condition, that is ux0 is equal to fx and utx0 is equal to gx. So this is the infinite case, you can say. So ux0 is equal to fx, so this will imply that f of x plus g of x is small fx. This is some equation number of 1 for this question. Next is utx0 is equal to some gx. So you have to differentiate this function u with respect to t. So this will be c1, and then you have to substitute t equal to 0. c1 f dash of x plus c2 g dash of x is equal to g of x, and this is your some equation number 2. Okay, so from here you have to calculate the value of fx, capital Fx and capital Gx in terms of small fx and small gx. So if you will do this equation number 2, integrate with respect to integrate equation number 2 from some x naught to x, where x naught some finite point, you can say, what will you get? c1 integration x naught to x f dash of s ds plus x naught to x g dash s ds equal to x naught to x gs ds. So this will give us, so c2 c1 f of x minus f of x naught. This is your first term. Now the second term, g of x minus g of x naught, and the last term, this will be x naught to x gs ds. So if you will rewrite c1 fx plus c2 gx, this will be equal to x naught to x gs ds and with positive sign C1 fx naught plus C2 gx naught. So this is your equation number 3. And what was your equation number 1? Equation number 1 was fx plus gx is equal to small fx. This is your equation number 1. Okay, so what you can do here, 1 can be multiplied with some C2 and minus can be done with equation number 3. If you multiply equation 1 with C2 and subtract equation number 3 from it, you will get C2 minus C1 f of x. Gx will be cancelled out. C2 times of fx with the negative sign x naught to x gs ds minus C1 of fx naught minus C2 of gx naught. Okay, and if you will rewrite it, f of x is equal to, with negative sign, C2 divide C1 minus C2 plus 1 by C1 minus C2 x naught to x gs ds, and the left part will be plus C1 divided by C1 minus C2 f of x naught plus C2 divided by C1 minus C2 capital G of x naught. This is the value of your fx. Now what will be the value of gx? So for the value of gx, what we will do, we will multiply the equation number 1 with C1 and we will subtract equation number 3 out of it. So when you multiply with C1, and then you will get C1 minus C2 g of x, and here this will be the quantity C1 fx with negative sign of this quantity x naught to x gs ds with negative sign f of x naught minus C2 g of x naught. So from here you will get the value of gx as C1 divided by C1 minus C2 fx. Here we have missed fx. So next one will be 1 by C1 minus C2 but with negative sign x naught to x gs ds with negative sign C1 by C1 minus C2 fx naught with negative sign C2 by C1 minus C2 x naught to x, sorry, here it will be gx naught, capital Gx naught. So from here you will get the value of capital Fx and the value of capital Gx. Next what we have to do, we have to substitute these values in our original solution, and original solution was uxt equal to f of x plus c1t plus g of x plus c2t. Now you know the value of f of x, you know the value of g of x, you have to substitute these values here. So what was the value of fx? Minus c2 by c1 minus c2 minus c2 by c1 minus c2 f of x plus c1t. The next factor will be 1 by c1 minus c2 from x naught to x, that is x plus c1t g of s ds. Okay, then the other quantity will be the constant terms, you can say, plus c1 by c1 minus c2 fx naught plus c2 by c1 minus c2 gx naught. Okay, next this gx term. So gx was c1 minus c1 divided by c1 minus c2. So this is fx, that is f of x plus c2t. Okay, and the other part is plus, or you can say with negative sign. This is with negative sign, 1 by c1 minus c2, and this will start from x naught plus x plus c2t gs ds. So plus c2 divide by c1 minus c2, this will be with negative sign, f x naught minus c2 divided by c1 minus c2 g of x naught. So from here you got this quantity, and if you will observe that these constant terms will going to be cancelled out, and you will left with the only term that uxt will be equal to, this is c1 by c1 minus c2 f of x plus c2t. Okay, and then the other one will be minus c1 divided by c1 minus c2 f of x plus c1t. Okay, and the other part will be 1 by c1 minus c2 x naught to x plus c1t gs ds with negative sign x naught to x plus c2t gs ds. So if you will observe here, so what you can do, you may rewrite this one as c1 divided by c1 minus c2 f of x plus c2t minus c1 divided by c1 minus c2 f of x plus c1t, and you may rewrite it as integration x naught x plus c1t gs ds without loss of generality, without loss of generality, let c2 is less than c1. Okay, this will help us in this following manner. You may write it x plus c2t2 x naught gs ds. Now you may combine these two integrals as uxt will be equal to c1 by c1 minus c2 f of x plus c2t minus c1 by c1 minus c2 f of x plus c1t plus 1 by c1 minus c2, and this integral will combine from x minus c2t x plus c1t gs ds. So this will be your, you can say, general solution. This will be is the solution of the given PD. Okay, so this is the solution of the given PD. If you will observe, this is nothing but the infinite case. But what was the infinite case? There is only one constant. That is, there is no both C1 and C2. There is only one constant. So that means there must be the infinite case must be the particular case of this case. So what you will do? you will do, since because C2 is less than C1, therefore we will assume that, therefore let C1 is C and C2 is minus. Okay, so from here, if you will substitute these values, you will get the solution uxt as, so c by c plus c, that is 1 by 2 f of x minus ct with negative sign. So this will be negative sign, or from, and there will be minus f of x plus ct. Okay, or you may also do the reverse case also. In the case, and if you will do the reverse case, there will be more benefit. Just a second, I think we have mixed some constant. So it was c2 by, in the fx it was c2, not c1. So minus c2 was minus c2, and from here we have replaced it as c1. So it was f of x plus c1t. So here it will be c2. Okay, so from here it will be just a typo, c2 c2. So we are putting c2 as minus c, so this will be plus sign. And next next part of the solution will be 1 by 2 c from x minus ct to x plus ct gs ds, and this is nothing but, this is the D'Alembert solution. D'Alembert's solution for infinite case, or you can say um, initial value problem of wave equation. So that means this question number 6, you can say a generalized version of this initial value problem of wave equation. So this is all about this week 9 lecture, or week 9 problem solving session. Now let me come to week 8 problem solving session. In this problem solving session, we left with two parts of the question that I would like to cover in this one. So if you will remember that in this scenario, there was a case left when x is equal to 3 by 2. Okay. So in this equation, let me recall first. So we have given this PD. Okay. And in this PD, we want to transform this PD into the canonical form, or you can say into the normal form. So although I have updated its solution in the solution PDF already, but I am just recalling the things here that we have not solved in the video session. So we left with that. So if you will observe here that for x not equal to 3 by 2, that is the maximum case covered by only this part only. So you can convert canonical form for major case. But what if when x equal to 3 by 2? So when x equal to 3 by 2, then your equation must be replaced x equal to 3 by 2 in the equation also. That we have not done in the previous class. So when x equal to 3 by 2, you are getting your dy by dx is equal to only one solution, that is y minus 3x. Okay, dy by dx are getting this value. Since x equal to 3 by 2, then you have to substitute here, that will be 3. So this will help to reduce or you can say get the easy transformation comparative to the highest transformation. So what we have taken xi to be y minus 3x. Now since we are getting only one transformation from the your given characteristic equation, you can say, so what will be the another transformation? So let us recall the basics. The other transformation should be like that, such that its Jacobian of xi and eta with respect to x and y must be a non-zero quantity. So we choose eta to be x, and we will calculate its Jacobian, which is coming out to be -1, which is a non-zero quantity. Okay, so that means our you can say our assumption of this eta is accurate. Now we have to proceed with this xi and eta. Again, by the chain rule, ux will be u xi and xi x plus u eta and eta x. So u xi x is -3, so -3 u xi plus u eta. Similarly, uxx will be, again you will differentiate u xi xi and xi x. Xi x is -3, this will be 9. Okay, then u xi plus xi y, that will be -3, and u eta eta y, that will be going to be again eta y will be 0, so with that will not contribute, so you will left with this only -6 times of u xi eta plus u eta eta. Let me just see from here also. So u xi eta and eta of x, that will be 3 times of this. Okay, so from here uy will be just a second please. So I think this should be -3 times of something, so that it will be cancelled out. We will see further. So if you will discuss about uy, so uy will be u xi xi y plus u eta eta y. So since this is your u xi y is 1 and eta y is 0, so it will be uy will be directly u xi, and uyy will be u xi xi. Now you have to calculate uyx or uxy. So this will be u xi xi. We are differentiating only this y with respect to x. Then xi x, that is -3. U xi eta and 1 -3 times of u xi xi plus u xi eta. This was our original given equation, but we have to think at x equal to 3 by 2. Then we will substitute here 3 by 2. This will be uxx plus uxy plus 9 times of uyy. So uxx was 9 times of u xi xi minus 6 times of u xi eta plus u eta eta. So from here, this should be, you have put this value, and uxy is -3 times of u xi xi plus u xi eta. So that means this will multiply by 6, 18 times of xi xi plus 6 times of u xi eta. Then the left part will be 6 times of x uyy, that is 9 times of u xi xi. So if you will add these values, these u xi xi terms will cancel out, and you will left with this u eta eta equal to 0. Okay, so that's all about this normal form of this particular case, that is x equal to 3 by 2, that we have left in the previous class. Now in the last question, we wish to get u xi eta equal to 0, but we are getting some ambiguity in this solution. So if you will if you have observed from here, what we have done, we have missed one term here. So let me go through that. First of all, you must try this one at your own, then I will discuss it sometime. So try this one. So let us discuss this one also. What happens in this case? We missed one term, that is why we are not getting our required canonical form. So I am here, I am again discussing it to mention what is that term. So if you will remember that from here our b square minus 4ac was 4, that is a positive term, and dy by dx will come out to be this minus sin x plus minus 1. So from here you will get your xi as y minus cos x minus x, and your eta as y minus cos x plus x. And you will, if you will calculate its Jacobian, it come out to be minus 2, that is a non-zero quantity. When you will calculate ux, so that will be u xi and xi x, and xi x is sin x minus 1 and eta x is sin x plus 1. So this will be your u xi and u eta in terms of ux, in terms of u xi and u eta. What if when you will discuss about uxx, so this will be sin x minus 1 whole square, u xi xi, and one term of this sin x plus 1 and one term of sin x minus 1, because of u eta x and xi x will multiply. So since it will repeating two times, so it will be two times of this and this. Next one is sin x plus 1 whole square u eta eta. Again you have to differentiate this also. These are the function of x, so this will be cos x u xi, cos x u eta. Similarly uy will be u xi, xi y, and u eta, eta y. Xi y and eta y are 1. So therefore this will be u xi plus u eta. Again when you will differentiate with respect to y, this will be u xi xi, u xi eta, u eta xi. And since we are working with the second order continuous partial order derivative, then u xi eta will be u eta xi. That will be 2 times of u xi eta plus u eta eta. Then the last term we have to discuss with uyx. So what we are doing, we are differentiating this with respect to x. So this will be u xi xi x, that is sin x minus 1 u xi xi. Again sin x plus 1 u xi eta. Okay. Next one term will be sin x minus 1 u eta xi plus u eta eta. So in case of u eta eta, you are differentiating with respect to x. So here there will be a term of sin x plus 1. Sin x minus 1 u xi xi plus 2 times of sin x u xi eta plus u eta eta sin x plus 1, that we have missed in the last class. Now if you will try to solve it, then here will be some 4 and this is sin x plus 1. These two terms that we have missed, because of that our terms were not cancelling out properly. When you will substitute it now, then you will get to this u xi eta and you will get to this your general solution of the PD. So this was happening. So I am just recalling this solution also. What is the value of uxx? Sin x minus 1 whole square u xi xi plus 2 times of sin square minus sin square x minus 1 u xi eta plus sin x plus 1 whole square u eta eta. But there was two terms also that we are writing it here. Okay. Next one is we have to multiply minus 2 sin x with uxy. So this will be 2 sin x into sin x minus 1 u xi xi. 2 sin x into 2 sin x, it will be 4 sin square x u xi eta. 2 sin x into sin x plus 1 u eta eta. And the last term is uyy, that is u xi xi plus 2 u xi eta plus u eta eta, that should be multiplied by cos square x. So cos square x I am writing 1 minus sin square x u xi xi, since it was with negative sign, minus 2 into 1 minus sin square x u xi eta minus 1 sin square x u eta eta. So from here, and the last term will be this ux minus cos x uy equal to 0. So these um, terms will cancel out, that we have marked from this yellow lines, and this green line will cancel out, and again this these three terms will also cancel out, and you will left with this u xi eta, that is coming out to be u xi eta equal to 0. From here, since it's partially differentiating with respect to eta equal to 0, that means the constant must be function of xi. Again you will integrate with respect to xi and some constant that is in term, then should be in terms of eta. So your solution will be phi xi plus xi eta, and in terms of x and y, this will come out to be, let me just rewrite it. So this is in terms of xy, that is in terms of xi eta. So this is your general solution of the given PD. One last conclusion that we have left with here, we were saying that is there minus 6 or not? There should be minus 6. Why? If you will see u xi eta eta x plus u eta xi, and here will be xi x. Okay, so here it was minus 3, so this will be 1 and this is minus 3, so you will come out to be 6 times of u xi eta. Okay, so I have covered the doubts of the previous class also. So if you have any query, then please ask, otherwise let's end today's session. Okay, since there's no inquiry, thank you. Let's meet in the next session, week tutorial, problem solving session of week 10, in the next week on same time on Tuesday. Thank you.